So this is finding the shortest distance part 2, and now we're doing weighted graphs. So the graphs that we looked at before don't have any distances written on them, and they're fairly simple. And what we want to do now is put distances on them. As soon as we put distance on them, distances are considered as weights, because now one edge is not the same as the other. So if I look at this graph, there's nothing that distinguishes all the edges, but what we want to say is that these edges have different values because they represent different distances. So that's called a weighted graph when we put values on the edges. And again, we're representing this map right here. This map is very complex, and it represents, how the trails curve around, and so it represents the spatial relation between the graphs. But in order to solve the problem, we're not interested in the spatial relations between them. We're only interested in connections and distances. So the first thing we did was take this map of Sleeping Giant and transformed it into a graph like this. So this graph now shows each of the nodes and the connections between the nodes and the distances between. So for example, this is a node number 39. It's connected to number 38 up here, number 40 down here, by distances of 0.7 and 0.04. And we'll have this graph somewhere else where people can get it in order to work on solving the problem. So don't worry that it's difficult to see here. But this is the type of graph that we need to make so that we're dealing only with the connections and distances and not with the irrelevant question of whether or not, for example, this path is wiggly. When you walk it, that might be important, but for finding the distance, that path that leads up to 38, for example, this wiggly path is just represented by, I think it's this straight line right here. It looks curvy, but it's really straight line right there. So this is the type of graph that we're interested in dealing with. So first we need to look at graphs that are a little bit more like that. So what makes this graph a little more challenging than the graphs before is that it has these weights on it, and also there's more than 2 odd nodes. Another thing that distinguished our simpler graphs that we dealt with here before is that there were only 2 odd nodes. So this graph we're going to find has more odd nodes. But the solution revolves around first establishing the degrees of the nodes and identifying the odd degree nodes. So for example, this node only has 1 path coming into it, so its degree is 1. This node has 3 paths coming into it, so its degree is 3. This one is a 4. This one has 3, so that's a 3. This one has 2 edges. This node has 2 edges, and this node has only 1. So those are our degrees, and the important thing for us to solve the problem is to just find the odd nodes. So we've now found that the whole problem revolves around that. So this node is odd, this node is odd, this node is odd, and this node is odd. So what we found before is that we find a solution by connecting the odd nodes. So I can look at these 2 nodes, and it seems pretty clear that I should connect these 2. And over here, though, I have to connect this odd node, and I have to connect it to this odd node because I've already connected this one to something else. So in order to do that, I need to pass through point B and then on over to E. So what this is now telling me is that I've now established an Eulerian circuit, a way to visit all the edges and not retrace, but really I am retracing. I'm retracing the red paths. In terms of Euler's solution, the red path is a new path, so I haven't really retraced a path when I come down here, mathematically speaking. But in practice, of course, it's really the same path and you're walking down it. So the key is to find ways to connect these odd nodes. So in this case, I've connected these pairs, and what I've connected is G to F and A to E. And by the way, I would not have to connect A to E this way. I could connect A to E by going up here and down here. Now, that would be advantageous if, for example, this edge were extremely long. So in terms of the graph, in terms of the actual map, maybe this path like wiggles around and it's really long. And then I would want to avoid this path. It means I'd really want to connect this way. So there's more than one way to connect the paths. To connect the odd nodes. There's more than one way to connect the odd nodes. So the first thing is, once we've established a pairing, I'm going to pair G with F, I'm going to pair A with E. I need to find the shortest way to connect G to F and A to E. It's clear that there's only one way to connect G to F, but A to E, there's more than one way to connect it, and I need to make sure the way I'm connecting it is shortest. So if I connected A to E by going up here, I'd be going 4, 2, and 2, that's 8. But if I connect straight across, that's 4 plus 1 is 5, so that's shorter. But just because it looks shorter on this graph doesn't necessarily mean that it is shorter, because if, for example, this edge were 5, then it would be shorter to go this way. So we're going to have to watch those distances. But the first thing is to establish our odd pairing. Once you've established an odd pairing, then there has to be a way to retrace the graph, to trace the graph without doing any retracing. So one way I could do that is I could go like this, and I could go down to C, and I could come up to B, and then I could retrace this one and go up here and then go like that and then come down and go back here. So I've started at A, I've ended at A, and I've covered all the paths. And so that's one solution. But one of the things that I've mentioned and that we're going to have to contend with a little bit is that once you have identified the paths that are going to be repeated, there is more than one solution that will repeat those paths. So the first one I showed you went A, B, E, D, C, B, E, F, G, and then it looks like it goes F, B, A. So that's the path that I first went, A, B, E, D, C, B, E, F, G, F, B, A. So that's the first solution. But even with this, just this one pairing, there's more than one solution. So here's a second solution. I could also go, instead of going straight through a B, I can turn down to C and then go up to D, and then maybe I will go out here and then back, and then go up here and then back, and come down and go out here. So that's a different solution that amounts to going A, B, C, D, E, B, E, F, G, F, B, A. So these are two different solutions using the same retracings, but what you can also see is that they are the same retracings. So for example, in this sequence, you could see this visually as well, but if you think symbolically, I repeated AB and BA in this solution, solution number 1. I repeated BE and BE, and I also repeated FG and GF. So the paths that were repeated were A to B, which happens twice, B to E, which happens twice, and G to F, which happens twice, right in a row. In the second solution, we still repeated the same paths, but in different places. So I still did AB and BA at the end. There's a reason why that sort of has to happen. And then I went EB and BE, and then we went FG and GF. So the same sets of pairs were repeated, but in a different order, because this one put BE and BE separated by D and C. This one put EB and BE together. So certain things, it's clear, have to happen. There's no way I can get to G without retracing FG. I have to go up F and back down to G. It's pretty clear that if I start at A, then I have to go out to B and then do whatever I'm going to do, and then I have to come back here. So it's clear that this particular path must be repeated, this particular path must be repeated, because they are terminal. These are terminal nodes. They end up here and they only have one path coming into them. So they're terminal nodes, they have to be repeated. What is not obvious from looking at the graph is that this is the other one that has to be, or even that there has to be at least one other path that's repeated. So the trick is to find those other paths in the middle of the graph that have to be repeated. So once we've established a pairing, and then we found a path using that particular pairing. Now, also using that particular pairing, we can find what the distance has to be, what the distance covered that I retraced was. So for example, in this particular pairing, to connect G to F cost me 1 additional unit of weight. You know, maybe it's a mile, maybe it's $1, who knows what it is. For mathematics, it doesn't matter. One of my favorite things about mathematics, the units don't matter because what we're talking about is not real anyway. From A to E, the distance you connected is 4 to 1, 4 plus 1. So we have 4 plus 1 there for A to E. So our total additional routing for this particular pairing is 6. So one thing to consider is, and this will be the difficulty in our big graph. This graph is a little bit simple because there's only 4 nodes. Now with 4 nodes, 4 odd nodes, there are 3 different ways to pair those nodes. So the other possibilities I have are that I could pair G to E and A to F, or I could pair G to A and B to F. So for example, instead of pairing G and F here, I could have paired G with E going through F, and I could have paired F with A. So it's sort of clear that that wouldn't result in the shortest route, but that's because this is a simple graph, and on a more complicated graph, it will be less obvious what is the shortest route right away. So let's say I paired G to E and A to F. So if I go from G to E, the minimum distance that costs me is 1 plus 2. So 1 plus 2, that's 3. I could pair G to E by going 1 plus 2 plus 1. 1 plus 2 plus 1 is 4. But I wouldn't go that way because that's a higher cost than going just this way, which is 1 plus 2. So that's pairing G and E. And if I paired A to F, I would pair A to F by adding 4 plus 2. Of course, I could go 4 plus 1 plus 2, but I don't want to. So 4 plus 2, that's that distance. So when I add up all these distances for this odd pairing, I have 1 plus 2 is 3 plus 6 is 9. So that's 9. So I can see that I have 3 different possibilities for pairing odd nodes. This one so far is better because the distance is only 6 when I add the distances for pairing the odd nodes. This pairing of odd nodes is worse because it costs me 9 instead of just 6. But I'll consider the third one, which is G to A and B to F. So if I go with G to A, I have to go 1 plus 2 plus 4, so that's 7. And if I do B to F, actually it's E to F, isn't it? I think it's E to F. E to F. Now E to F might look initially profitable because connecting E with F only costs me 2. And that's cheaper than connecting E to A. But the problem is that it would then force me to connect G to A, which is longer. So now I have, for G and A and B and F, E and F, I want to say, 7 plus 2, which is 9. So now I've considered every possible pairing of odd nodes, and the best pairing is G with F and A with E. So the shortest route is any of the solutions. Here are 2, but there are probably more. Any of the solutions that retrace this particular pair of routes is going to be shortest because that's the shortest way to pair the odd nodes. And that's the key to solving these problems. What's going to make it difficult is we found that there are 3 ways to pair these 4 odd nodes, because basically if I start by looking at node G, I can either pair node G to E, or I can pair it to, I'm sorry, that's F, isn't it? Yes, it's F. All right, so I can either pair G with F, or I can pair G with E, or I can pair G with A. So if I just look at that node G, I can pair it with any of the other 3 odd nodes, and there are 3 remaining odd nodes because I had 4 altogether, and G is one of them. All right, so there are 3 ways to pair 4 odd nodes. So if I have 4 odd nodes, then there are 3 ways to pair them. Now, I'll just let you know that if we had 6 odd nodes, and by the way, there cannot be 5 odd nodes, there has to be an even number of odd nodes, and that's a related mathematical theorem that we won't go into right now. But if there were 6 nodes, then what you would have is 5 times 3 times 1, which is 15 pairs. This is 3 times 1 pairs, which is 3. Now, if I have 8 odd nodes, then what you do is we go 1 less than 8 is 7, and we have to go 7 times 5 times 3 times 1. Well, 7 times 15 is 105. So you can see how the number of possible pairings gets large very quickly with the number of nodes. And our lovely graph has 30 odd nodes. With 30 odd nodes, what we have to do to find the number of possible pairings is we'll just clear that. We're going to start with 29, and we have to go 29 times 27 times 25. So what we're doing is multiplying all of the odd numbers that are less than the number of nodes there are. So we're up to 17, 15, 13, 11, 9. My 11 became a 1. So 11, 9, 7, 5, 3. And I don't really have to put the times 1, but I can't resist completing the pattern. And then when I find out what that equals, it equals 6.19 times 10 to the 15th power. So that is 6.19 times 10 to the 15th, or 6.2 million billion possible ways to pair all the odd nodes. This is why solving a difficult graph like this is normally done not just by a computer, but by a very large and fast computer that would go through and consider every possible pairing of nodes. Now here's the advantage that we have as human beings over computers. A computer would have to check all three of these possibilities to know which one's the shortest. But using our intuition and our visual processing, we were able to immediately decide that this would be the shortest pairing. So using our visual processing and our intuition, which are incredibly powerful computing devices, we won't have to consider the 6.2 million billion possible combinations because, for example, on this map, it's very obvious that we're not going to take this node here and pair it with this one down here. And there are lots of other absurd pairings that you would never do because you're a human being and you're a lot smarter than a computer. So our challenge is going to be to connect the odd nodes on this map using the shortest possible distance. And again, some of these are going to be obvious, like this one has to be retraced, but there are others that are less obvious. So what we have to stay focused on is that the task is to find ways to pair the odd nodes that have a total cost that is least. And that is the approach to finding the least distance through a complex map like we are about to do.